Hello there. Once again, we have another fascinating circuit. This one is an anti-log circuit. It's one of the series that I'm making on log anti-log circuits. And this is the fourth lecture, by the way. This circuit will provide a VO that equals 10 to the power Vn. So without wasting much time, let's start discussing the components of the circuit first. We get this part in here around op amp A1A that deals with the reference current. And the reference current is made by the very basic way. You got a 15 volts over there. You got your zener, which is not just a regular zener. I believe this is a precision voltage zener. Provides about 6.9 volts. Okay. You got the resistor in there, okay, which supplies the current to the zener and to our circuit. Okay. And if you're going to know what that current is, simply just deduct that 7 volts out of the 15. So you get about 8 volts. Your 8 volts divided by 2.2K, that you get your current that supply our circuit and our zener, and you have to keep that zener in that conduction state. Anyway, getting your 7 volts in here, or 6.9 volts in there, okay, divided by the 70K, you get your 0.1 milliamp or 100 microamps that you get. This is our reference current. And the duty of this op amp is to make sure that you get your virtual ground in there. So applying a positive voltage in there would imply that you have a very negative voltage in here, okay? And that negative voltage will force the VPE in here, or Q1A, to start conducting, and it will conduct that current exactly that equals to the 100 microamps, and therefore you get your virtual ground there. And that 100 microamps flowing through Q1A will set a VBE that corresponds to the 100 microamp or to the 0.1 milliamp. So you've got our VBE that corresponds to the 100 microamps. And in this area in here, we have the two resistors, the very familiar and noticeable circuits. So whenever we are dealing with the log to the base of 10, or dealing with the power of 10, okay, or any power raised to the 10 to the power raised, whatever it is, you're going to get those familiar two resistors in here. Sometimes this way, sometimes reversed. So in this case, since you want to find 10 to the power Vn, those resistors are reversed, and you got your 15.7K in here, okay? And you get your 1K in there. And that has to do with the number of 10. Log of 10 or 10 to the power of whatever. You got to have these combinations, or they have to be, let me see, how can I put it? Okay, you can change the value of these resistors anyway, but they have to have the same ratio, which is 1K to the 15.7K. In case you want something to the log to 8, or you want to have log to the 4 instead of 10 or natural, whatever, you just reselect those two resistors. And what else do we have? We have a Q1B in here. That one that is responsible for generating a current, okay, that corresponds to the difference between Q1B and Q1A. I will discuss that further. And you get your other op amp in here, which is the A1B, okay, that converts the current that was generated by Q1B back to a voltage, okay. And you get your output in here, which is VO equal 10 to the power Vn. Okay. In order to understand the circuit, it's better to apply numbers to it. Okay. And like we said before, we are always looking for the difference between the VBEs in order to take that difference, convert it back to a current, and feeding it to an amplifier or to an op amp. So that's what we are doing. And we're going to start by applying a 60 millivolts in here. Applying a 60 millivolts in here, sorry, we're going to start by applying a 1 volt in here. Why? Because we want to have something like VO equal 10 to the power of 1, which equals to 10 volts. So we apply in here 1 volt to get our 10 volts. Applying a 1 volt in here, you get your voltage divider between the 15.7K and the 1K. That gives you a 60 millivolts across the 1K resistor. And by the way, that voltage has to be negative, can't be positive. So we are applying minus 1 volts in here. So you get your minus and plus as the polarities indicate, which is a minus 60 millivolts. And what does that mean? Applying 60 millivolts to the base of this transistor in here. That means you got your VBE in here equals to whatever VBE that caused by the 100 microamps, okay, and pulled down by a further 60 millivolts. That, in turn, okay, will force VBE of this transistor, okay, to have the current of the 100 microvolts plus whatever the 60 millivolts that applied to it. Those both, they can cancel when you have 100 microvolts in here, 100 milliamps in here, 100 milliamps in here, they cancel. You're left with your 60 millivolts across that transistor. Okay. So let's say that again. Okay. Having a minus 60 millivolts across this resistor will force the emitter input of both those transistors to be minus 60 millivolts. Okay. And that means you are having a VBE in here. The difference between this VBE of this transistor and that transistor will be 60 millivolts. The VBE of transistor Q1B is 60 millivolts more than Q1A. And don't forget that it's tied to the ground, while this one is floating. So therefore, they cancel, the VBEs cancel with each other to lift with your 60 millivolts in here. Having a 60 millivolts in here, and based on all the derivations that we made before, okay, and let me just repeat that equation once again, okay, when you have a delta VBE between two transistors, they are matched pair, by the way, matched transistors, 16 millivolts in there means that this current will be 10 volts. IC in here will be 10 volts that IC over there for the I reference. And that based on the equation, that delta VBE between the two transistors equal KT over Q, the natural logarithm of IC Q1B divided by Q1A. So that means this current will be 10 times that current, okay? Having the current of 10 times the 0.1 milliamp means it's going to be 1 milliamp. 1 milliamp going through the 10K resistor will give you your 10 volts. So having minus 1 volt in here is giving you a plus 10 volts over there, okay? Another example also, let's clarify things better. Another example, let's apply in here a 0.5 volts. And as we know, VO equal 10 to the power 0.5, what means it's under the root square. And the root square of 10 would be equal about 3.2 volts. So applying a 0.5 volts in here will give us a 30 millivolts in here, minus and positive. Okay. 30 volts. And like we discussed before, that means this VBE will have 30 millivolts more than that one over there. Okay. And that will give you a current of about 3 times that one in there. I believe it will be about 320 microamps. Okay. And that in turn will give you a V out of about 3.2 volts, which is the root square of 10, or which is the 10 raised to the power 0.5. Okay. And they call it sometimes exponential amp or anti-log amp. And in here you see a few derivations in here. Save derivations if you are interested in more of these numbers. And I have about 20 lectures on transistors before, and this is the fourth of the anti-log. You can go back to these lectures if, in case you are missing some of the information. So I can't keep repeating myself. So you can go back and see how some of these values, some of these numbers are taken. Okay. And on the side in here, see some mathematical derivation. And in case we can see something else too, a further numbers and further discussion. Let me see. In case somebody is interested in more derivations. Okay. I'm gonna roll these calculations slowly. In case of somebody is interested in following that, just pause the frame and get whatever information that you need. I'm not going to discuss this equation fully. Okay. I believe that's about it. Thank you for watching and have a nice day.